No.
Okay, now we're recording. Okay, guess why we're talking about solutions?
Because you're going to solution.
No, it is, by the way, chapter 11 in your book. You may need further edification. Go to the book, chapter 11. Why do we talk about solutions in chemistry? For fun is not correct. What is chemistry all about?
Stuff.
Now, make stuff. Reactions. What do you think it's easier to react? A couple of solids or a couple of solutions?
I'm going to go with solutions.
You're going to go with the right answer, which is solutions. So one of the things we need to talk about when we're talking about solutions is how to describe them. And one method to describe them is via their concentration. And their concentration has terms that you're familiar with and terms that you are not familiar with. I believe you've all seen molarity. The unit, the variable is called M. Mass percent, otherwise known as weight percent, percent by mass. The mole fraction, we touched on this just briefly. I'll go forward and redefine that for you in a little while. And then molarity's evil twin, molality. Why would someone do this to you? One letter difference. That's it. And the variable, same letter, only it's in not caps. Okay, and normality, which is important to no one except old people like me. Normality is kind of an archaic unit of concentration, but still acids and bases are still sold by the normality, and so when we get an acid or a base, people come to me like, I don't even know what this is, and I think to myself, good thing I'm old, because I do. But you have to know just one or two things about it. All right, let's go through this. I'm going to annotate a little bit. If I write, I think probably you should write as well. Molarity is the number of moles of solute per liter of solution. Ladies and gentlemen, none of these formulas will be given to you on your green sheet, so you need to make sure you have it right in your brain, and you need to keep the variables straight. Solute, moles of solute per liter of solution. This is temperature dependent. Someone who is awake, tell me why it is temperature dependent.
Because the volume depends
The
on
liquid solvent can
temperature.
expand and contract with changes in temperature.
You are so smart.
You bookworm.
Indeed, it can. All right. So it is not a constant ratio of the solute solvent particles, but it is when you're doing stuff at standard state, room temperature. Then this is the go-to unit of concentration. We like that. Here's an assumption that you should use when you are solving problems. This will make you happy in a little while. If you were to say that something is 3.75 molar, that is equivalent, boy, that's better, isn't it? That's equivalent to saying there are 3.75 moles of solute per 1 liter of solution. Duh. Really.
That's a nice assumption.
At first blush, people don't think about that. Okay. So now we're going to go to mass percent. You can have a percent by volume, a percent by mass to volume. We're just going to talk about percent to mass. And that is defined as the mass of the solute over the mass of the solution. Once again, of the solution times 100%. Here is the second assumption that you can make to help you solve problems. If something is described as 28% by mass, that would mean that you have 28 grams of solute in 100 grams of solution. We got that. Now, mole fraction is a ratio of the number of moles of a given component to the number of moles of solution. Oh, that's very unhelpful, isn't it? Here we go. Because you can describe this in two ways. Here's the most common way. The mole fraction of the solute is equal to the moles of the solute divided by the moles of the solute plus the moles of the solvent. If you were awake today, you would see that this is a unitless concentration. Okay, now somebody who is sort of awake can tell me what that formula is.
Moles of solvent over
The
moles
same
of
thing.
solute.
Uh-huh.
Look at this guy, he's getting all the answers.
Yeah, it is. Setting the bar for the second semester.
Can I go to sleep then?
No, not until tomorrow. Okay, here's an assumption-ish. It's not an assumption, but it will help you solve these problems. The mole fraction of the solute plus the mole fraction of the solvent. It better be 1. Yep. All right. Okay, now we're going to get to molality. Where would you use molality in place of molarity?
Well, it's a solid.
The
It's
question
not
asked for it.
temperature dependent.
When, okay, I'm
When it's
thinking
not a-
about
when it's not a
you
solution.
being big boys and girls and having a JOB. Okay, so if you had a job, I don't even want to know. Don't tell me who that person is. Okay. Oh yeah. All right. If you had a job as, I don't know, a petroleum engineer, that guy, it might be helpful to talk about concentration in terms of something that is not temperature dependent. Downhole in a 10,000-foot well is a little
Oil.
hot.
What?
If you are lucky, it is oil. But okay. So you need something that would not change when the temperature changes. If you on the surface had something that was had a molality of 1.72, downhole, it would still have a molality of 1.72. Yeah. Okay then. Now the only thing I need to caution you is this is the weirdo. Well, actually, I should have done this.
It's also applicable to Kroger.
Okay. Pretend. How could this be applicable to Kroger?
Well,
Well,
You
it's
have to
really
work- you
cold
have to
in
work at
Kroger.
there's a lot of freezers, and a lot of.
You have to work at Kroger.
We have to
to
determine the
understand.
molality of all the vegetables and produce.
You have a little molality in Kroger.
All right. Okay, here we go. Pretend I circled this part because this is what I meant. Okay. Normality, really quickly, is the number of equivalents per liter of solution. Great. What is an equivalent? Nothing your little self needs to concern about except for this. It's used for acid and bases. It's a mass of acid or base that can furnish or accept exactly 1 mole of protons. Oh, I don't really care. Nope, you don't. This is the only thing that could be moderately useful to you. If you take the molarity of something and you multiply it by the number of protons or the number of hydroxide ions that it can furnish, that is the normality. So if you look at this little chart, HCl has 1 proton to throw into the mix, so something that is 1 molar HCl would be also 1 normal. H2SO4 sulfuric acid has 2 protons to throw in, so something that is 1 molar would be 2 normal. NaOH has 1 OH ion, 1 molar equals 1 normal. Calcium hydroxide has 2 hydroxides, 1 molar equals 2 normal. Good?
Why do you divide it by that number to get the mass, equivalent mass?
Where? Here?
No, the middle.
Oh, this?
column, yeah.
That's just, you just do.
Just accept it.
Just. Okay, because then I want to go on to this. You may say, duh, but the density of a solution, by the way, this is how you abbreviate solution. The density of a solution is equal to the mass of the solution over the volume of the solution. Huh.
That's no different.
Why?
Broken heart.
Yeah. Okay, you just wait. I'm telling you, these are just a tad trickalicious. Okay. Would you press the record button? That's all I want to record.